All right. Where are we? This is the unit 4 portion of our trig final exam. So it's lots and lots and lots of graphing on this one. This first one we did in the last video. Now this next one, it's the same thing. So I'm not going to make a video on this one. I'll do the problem and I'll post the key in its entirety after all of this, but I'm just going to do one of these because it's the same exact process. But I am going to do this one because slightly different. All right, notice how it is a secant. All right, it is 3 times the secant of 4x. These are those reciprocal identities that we have here. And the key for graphing secants is first graphing the cosine function. So if we think of the cosine function, all right, it looks like this. I'm going to do the cosine. I'm going to do it all in black here. All right, it comes down, it hits 0, it comes back up through 0, and then it ends at 1. All right, so this is just like y equals the cosine of x. All right, now if you want to think about the secant, right, secant is equal to 1 over the cosine. Right? So, if there is a point where we have a 0, like cosine of x is 0, and we know that is true in a couple of spots. We know that's true. Oh, where is that? At pi over 2 and 3 pi over 2, which are these 2 points right here. Right? Well, we end up with 1 over 0, and we do not like that as mathematicians, right? Having 0 in the denominator dividing by 0 generally leads to bad things. So if we look at our cosine function, we have to identify those zeros. And then what we do is we look at those zeros and we draw some vertical asymptotes. Right, vertical asymptotes, we describe those as dotted lines through our graph. Now, they're not actually part of the graph. They're more as a visual aid for people who are looking at this. Now, the secant function, y equals the secant of x, has very much to do with this cosine, right? Basically, what happens is we look at the cosine, and anywhere we see these maximums or these minimums, we basically draw some U-shapes. All right, so it's going to look like this. All right, it touches, well, it doesn't actually touch the asymptotes. Remember, it gets really close to them, but never actually touches. Right, and that red portion is the cosecant. I could get rid of that black cosine area in the middle, and just what remains now is what the secant function looks like. All right, but it's really hard to graph this thing as is. So whenever we have a secant or a cosecant function, we graph the cosine first, and then we put in those asymptotes in the appropriate spots, and then we kind of make those U shapes. Right? So that is what our secant function will look like. And then, of course, we have all of these phase shifts involved. All right. So let's just look at this first one here. We have 3 times the secant of 4x minus 5 minus 5 pi over 6 minus 1. Which one do I want to do? I'm going to do this one because there's a negative 3 there. On the last problem, we did not have the amplitude was positive, so let's just do one with a negative, just kind of figure out what that looks like here. So I'm going to start out, so I'm doing number 4 now, not number 3. I'm going to start out just listing out my A's, B's, and C's. All right, so A is -3. All right, now keep in mind, remember, A we associate with the amplitude. The amplitude is always a positive number. All right, so I know A is a -3, but the amplitude is just going to be +3 here. All right, the B value is 5. Our C value here is 2 pi. And D value is equal to -1 or -1, however you want to look at it. So I'm going to take all these. I'm going to Move these over here. Kind of get them out of the way. All right. We can identify everything A, B, C. So I guess before we even do anything, we can draw in that midline. We know the midline is going to be one space below the x-axis. All right, so I'm just going to draw that in. All right, this is my midline. The amplitude, 3 spaces above and 3 spaces below. All right, so I'm just going to go 1, 2, 3. So that's my maximum. And then the minimum, we're going to go 1, 2, 3. Right? I shouldn't call this a maximum or a minimum in this case, and I'm going to explain why at the end here. Because keep in mind, I mentioned this, on that whole previous page, we don't want to graph the cosecant yet. We want to graph the sine for now. So we're just going to pretend that this is a sine function. Right? So first things first, identify the amplitude, identify the vertical shift, which is what we did. So the vertical shift we said was down 1. You could say -1 if you wanted to. The phase shift is going to be next to the period, all that good stuff. So here, let's start by graphing the period, or I guess identifying the period. We know the period is equal to 2 pi divided by b. Right? Well, we know what b is. We said b was 5. All right, so the period here is 2 pi all over 5, 2/5 of a pi. All right. So let's identify our 5 kind of important parts. Before we do any phase shifts, all right, it starts at 0, right, and it completes one cycle, one period at 2 pi over 5. Right, so that means halfway between them is 1 pi over 5. And then halfway between 0 and pi over 5 is pi over 10. Right, and then the very last one here should be 3 pi over 10. Now, I talked about like unreducing fractions on the previous video. So if you want to do that, it's not, I kind of like to do it. It's not, mathematically, I don't know, appropriate to do, but it's not hurting anything. Because for me personally, it does make it a little bit easier to kind of see a pattern here, right? We're going 1 pi, 2 pi, 3 pi, 4 pi, and then it's all over 10 now. So that to me makes sense. If you don't like that, then you don't have to do that. If you want to keep them as reduced fractions, then by all means, go ahead and do that. But now we need to look at the phase shift. I'm going to put PS here. All right, and the phase shift is that negative C value over the B value. All right, so we know C is 2 pi and B is 5. So the phase shift here is negative 2 pi over 5. And if I wanted to make life easier, everything over here is in terms of tenths. So I'm going to call this negative 4 pi over 10. All right, so that is my phase shift here. I am moving everything backwards, I guess for you guys would be that direction. 4 pi over 10 units. All right, so every single one of these values we need to subtract. We need to subtract 4 pi over 10. All right, so I'm going to go ahead and do that. I'm going to draw my 5 individual points. And so this first one here, this is negative 3 pi over 10. Then we're going to have negative 2 pi over 10, and so on and so forth. Negative 1 pi How about negative? What did I do wrong? I'm already messing up. Uh, Pause. Let me start over. I started on the wrong spot. This is negative 4 pi over 10. This is negative 3 pi over 10. Negative 2 pi over 10. Negative 1 pi over 10. And then the last one is 0 pi over 10, which I'm just going to call 0. All right, so this entire function ends up being on the left side here of our axis. So here's what I'm going to do. I'm just going to draw on 5 points here. Here's 1, here's 2, here's 3, 4, and 5. All right, so those are my 5 points. So if you did want to graph these and maybe unreduce these, if you did want to unreduce them, make it look a little bit more, appropriate, you could do that. I'm going to leave them as negative 4 pi over 10. I wouldn't take off points for something like that. So if you guys do that, that's okay. Coach Hogg might not agree with me on that one, but he'll forgive me. Negative 3 pi over 10. Negative 2 pi over 10. Negative pi over 10. And 0. Right? So those are my 5 points. Now this is a sine function. We know the sine function starts at our midline, right? But we have this negative sign right here, right? What does that negative a do? That reflects the whole thing. Right? So like, for example, a normal sine looks like this. Right? A negative sign, if we just had like a negative 1, it looks like this. Right? It starts and stops at the same spot, but it's flipped upside down. Right? So we don't want to go up first. We're going to have to go down first, and then we hit that midline. Then we hit our maximum, and then we're back down at the bottom. All right, so this is what our sine function looks like. Try that again. It's going to look like that. All right, this is our sine. So here, let me change my colors here. So we're nice and color coded. We're going to do a sine. All right, but again, we don't want the sine. The end goal was to graph the cosecant. So what we have to do is identify those 0 points. Those are our asymptotes. I'm already using all my dotted lines here, but that's all right. All right, so anywhere that your graph crosses the midline, make a dotted line. And then just kind of complete the U-shapes, right? So the minimum on this sine becomes kind of the maximum on this cosecant. It's going to look like this. We're only graphing one period of this, so there we go. Right, that purple part is the one we want. All right, there is another one, so right, if we wanted to think about it, it does do this. It does kind of go on forever, right? But since we're only graphing one period, I don't really care about these over here. Okay. So the period on this thing we found earlier, I guess if we want to fill in everything, this is 2 pi over 5. The phase shift was negative 4 pi over 10. The domain is not going to be all real numbers, nor will the range be all real numbers, because keep in mind, we're looking at the purple one. The purple one skips all of these y values here. All right, this one, it looks like we're going up to 2, and this one is down at -4. Right? So your range on this, we cannot include -4 to 2. So here's what we're going to say. We're going to start at negative infinity, right? Those arrows point down, right? That says we're going down forever. And then it goes all the way up until it hits this maximum point right here, which is at -4. So we're going to say we go from -4 infinity to -4. And then we put this little u. That's called a union. That basically means we're going to skip over a whole bunch of numbers until we get to the top of our graph. And that's going to go from 2 to infinity. Right? So we're going to put brackets around the inside ones and then parentheses around the infinities. Now, the domain, this is where it gets a little tricky. Look at those asymptotes. Right? Where are those asymptotes? There is an asymptote here, here, and here. So we have to kind of come up with a pattern for these. If you notice, the 2, 4, if we had kept going, it would have been 6, then 8, 0, then +2, +4. Those are all even numbers. So the domain here, we're just going to say x cannot be equal to, let's say, multiples of 2 pi over 10, or pi over 5 if you wanted to think of it like that, right? We can have anything else. You could have 1 pi over 10, 1 pi over 20, 3 pi over 7, whatever. As long as it's not a multiple of 2 pi over 10, we'll be okay, right? Anywhere we have that asymptote is bad. So we have to take that out of our domain of our x values, of our possible x values. If we plug 2 pi over 10 into this equation, the calculator is going to say error. All right, so we cannot have those. But there we go. That is how we graph cosecant and secant functions. So in the last video, we graphed a sine function, all right, just a normal sine function. And then in this video, we graphed a cosecant function. So when I'll just post the answer keys here. I'll fill in the other 2 problems that I skipped. But they are very, very similar, the same exact process for these. All right, I will do this next one here, but this might take a while, so I'm going to make this in a separate video. So we'll see you guys in the next one.